Do you ever wonder how amorphous lumps of material are turned into the everyday products which surround us? Let's find out. In this video, we're going to talk about manufacturing processes. There are 6 main categories of manufacturing processes, which are forming, casting, molding, joining, machining, and additive manufacturing. Each one of these categories contains a large number of different manufacturing techniques. There are a lot of different factors which need to be considered when selecting the right manufacturing process. This includes the material you are working with, the geometry of the object, the number of parts you are producing, tool and material costs, and required levels of automation, to name just a few. Let's look through each of the 6 categories in detail. Forming involves applying forces or pressure and plastically deforming the material to produce the desired shape. It is typically used for metals. Most forming processes can be done when the metal is either above or below its recrystallization temperature. This is known as hot or cold working. Hot working makes it easier to plastically deform the metal, but cold working causes strain hardening, which increases the strength of the material. 3 common forming processes are forging, rolling, and extrusion. Modern forging is done using machines. In closed die or impression forging, the metal is placed between top and bottom closed dies. Repeated strokes from the hammer are used to cause the metal to flow into the shape of the dies. Objects produced using forging can have improved mechanical properties compared to objects which are cast, but it can be difficult to achieve tight tolerances using forging, and the required equipment can be expensive. Extrusion is a continuous process which involves placing hot metal in a chamber and using a ram to force it through a die, producing a long object with a constant cross-section. Extrusion provides an excellent surface finish and can achieve very tight tolerances, but it is only suitable for producing 2-dimensional shapes. Rolling is probably the most commonly used forming process. It involves passing metal between 2 or more rollers, which apply pressure and reduce thickness. More complex products like I-beams can also be manufactured by rolling. Rolling can result in improved mechanical properties and can be automated, which makes it good for large-scale production, but tooling costs tend to be high and it can't be used to produce very complex shapes. Let's move on to the next category of manufacturing processes, casting. Casting involves pouring molten metal into a mold and allowing it to solidify. It is what we call a primary shaping process. A secondary process, such as machining, is typically needed to achieve the desired surface finish. Like forming, casting is most commonly used for metals. 3 common types of casting are die casting, sand casting, and investment casting. In die casting, molten metal is forced into reusable metal dies at high pressure. Once the molten metal has solidified, it is removed from the mold. Die casting is mostly used for non-ferrous metals like aluminum and zinc, which have low melting temperatures. It provides an excellent surface finish and can achieve very tight tolerances, but startup costs tend to be high, so it is only really suitable for large production runs. In sand casting, a pattern is used to create a single-use mold from damp sand. The sand is typically contained in 2 mold boxes called the cope and the drag. Molten metal is poured into the mold through a channel formed in the sand. When the metal has solidified, the cast object can be removed from the sand. Sand casting can be used for a wide range of metals, including those with high melting temperatures. It can produce large and complex parts, and initial costs are very low, making it good for small production runs. However, it provides a poor surface finish and is not as accurate as other casting processes. The last casting process we will look at is investment casting. Several wax patterns of the same object are created and attached to a sprue. The wax tree is dipped into a slurry to create a ceramic mold. Heat is applied to melt out the wax. Molten metal is then poured into the ceramic mold. And once the casting has cooled, the mold is broken off. Investment casting is good for parts with complex geometry and can achieve tight tolerances, but it is an expensive and time-consuming process. Molding is very similar to casting. It involves shaping a liquid or pliable material using a mold. Most of the time, molding is used for forming plastics. Typical molding processes are injection molding, compression molding, and blow molding. Let's look at the first two. Injection molding is the most commonly used manufacturing method for plastics. Polymer granules are fed into the hopper, and a screw is used to pass the material through a heated cylinder before it is forced at pressure into the mold. Injection molding is mostly used for thermoplastics, which are polymers which soften when they are heated and harden when they are cooled. It is a very fast process and can be fully automated, meaning labor costs are low, but startup costs are very high due to the expensive molds, so it is really only cost effective for large production runs. Compression molding involves placing a precise amount of material into a mold. The mold is closed and pressure and temperature are applied. Compression molding is mostly used for thermosets, which are polymers which irreversibly harden when heated. Tooling costs are relatively cheap, making it good for small production runs, but it is quite a slow process and is not well suited for complex designs. So far, we have only looked at material deformation processes. Machining is a material removal process, where a tool is used to remove material from a larger object. It is often used for secondary shaping, when the part has already been formed using a primary process like casting. Machining can be used for a wide range of materials, including metals, plastics, and wood. Examples of machining include drilling, turning, and reaming. Drilling is the cutting of a normal circular hole by pressing a rotating drill bit through a solid object. And turning is the use of a cutting tool to shape a rotating workpiece. Let's move on to the next category. Joining involves combining multiple separate components into a larger assembly. Like machining, joining is a secondary process. Welding, riveting, brazing, soldering, and fastening are all different types of joining processes. Welding uses extremely high heat to fuse distinct metal parts together. Unlike soldering and brazing, the base metal melts during welding. The final category is additive manufacturing, which involves adding material to build up the desired object, typically one layer at a time. 3D printing, selective laser sintering, and vat polymerization are examples of additive manufacturing techniques. For 3D printing, a computer is used to successfully build up an object layer by layer. 3D printing is a slow process and the range of materials which can be used is limited. As a result, it tends to be used for prototyping rather than for mass production.
Hi, my name is Jeff Van Kuren. I'm the value stream leader of Thompson and all molded products here in Elizabethtown. And I'm here to demonstrate a little bit about how our molding works. So, molding starts by the pellets that we buy called resin. Here's an example of that. All plastic parts start from this. They're brought into a hopper and they're dried to certain temperatures and certain dew points. Now we're going to move around to the other side and show you what else happens. So after the resin has been dried properly, it's pulled up into this very small what's called hopper, which goes into a feed throat, which goes into a barrel. What happens is the pellets go in, the pellets melt as the screw goes back. And as you can see here, it'll go all the way back to the specified size. And that solid pellet has now become liquid plastic here. At that point, it's injected in and through the mold and formed, and that's what makes the part. So as it's injected through, the controller that you see here will regulate the pressures, the times, the temperatures, and all the other variables inside of this to make an acceptable part for our customers. As that goes through and as that completes, it'll form into a solid form inside the mold again. Once that's done, it'll eject the parts out and they'll be ready for shipment and or assembly. That's how molding works in the Thompson department here in Elizabethtown, North Carolina. Thanks for watching.
Casting process. In this video, we are going to see about casting process. It consists of pattern and sand. Casting is the process of producing metal component parts of desired shapes by pouring the molten metal into a prepared mold of the shape and then allowing the metal to solidify. The solidified piece of metal is known as casting.
Hey guys, welcome back to the channel. Metal objects surround us, from the chairs you sit in to the vehicles you drive. Metals are so important that humanity advanced from the Stone Age to the Bronze Age and from the Bronze Age to the Iron Age due to the discovery of new metals. Even though these metals were discovered much earlier than the advent of the respective ages, the methods of working on them were not developed. Almost all metals are hard solids, which make them impossible to work on. So how do we change their shapes, size, texture, and form to our required way? This is done by various metallurgical processes. The metal is made soft by bringing its temperature close to its melting point and then shaped. This is called forging. When the metal is melted by bringing it to its melting point and then shaped, it's called casting. Different metals retain their hardness in different manners with different procedures. A good example for this statement are swords. Iron or steel swords are hardest when they are forge-shaped, whereas bronze swords are strongest when they are cast. In this video, we'll talk in brief about forging and also the types of forging techniques used. Forging is among the oldest of the known metalworking processes. As we discussed, during the forging process, the metal is heated to very high temperatures and then shaped with the help of external forces. In the olden days, they were done by a blacksmith with the help of an anvil and hammer. Later, the blacksmith hammer was replaced by trip hammers. The trip hammers channeled the power of downflowing water and used it to lift huge hammer heads. This vastly increased the size of metal that can be worked on along with the speed of production. These trip hammers are the basis for all modern industrial forge hammers, which are powered by hydraulics, electricity, or compressed air. These hammers have a reciprocating weight of upwards of 1 ton. To give you a small idea of how big these hammers can get, we'll show a picture of one of these hammers. The Crusoe steam hammer, built in 1877, is 25 feet high and was able to deliver a blow of up to 100 tons on the workpiece. Forging is done to increase the strength of a metal. This is especially true for iron, as forged iron is much stronger than cast or machined iron. The disadvantage of forging is that it is not applicable to all metals. This is the reason why you'll mostly hear about cast aluminium but not forged aluminium. Forging is broadly classified into hot forging process and cold forging process. Just like the name suggests, the hot forging process is when the metals are plastically deformed above their recrystallization temperature. In cold forging, the metals are shaped in the ambient temperature, and this is usually below their recrystallization temperature. Cold forging is most commonly used to make small metal items like screws and nails. It is also called a chipless forming process, as it often requires no machining to be done. The biggest advantage of the cold forging process is mass production. Because of this, the process is most commonly used to mass produce small components like screws, bolts, and nails. The process also requires very little finishing work on the end product. This also saves money to the manufacturer and is economical. However, this process cannot be used for complex shapes. There is also a chance that the finished component tends to have residual stress in it. The next type of forging process is hot forging. In hot forging, the raw material of metal is heated to very high temperatures and then shaped. There are many types of hot forging processes. We'll be having a detailed discussion of these in our next video. Until then, take care and bye.
What are joining processes? Joining processes are the processes that are used for joining metal parts and metal fabrication work. It consists of 4 types: A. Welding, B. Soldering, C. Brazing, and D. Adhesive bonding. One of the only important joining process is welding. It is classified into 5 important types, namely gas welding, arc welding, resistance welding, solid state welding, and thermochemical welding. In general, welding has a large number of advantages, such as mechanizability, near metal strength, maneuverability, and low cost, which easily overshadows its disadvantages like harmful emissions, skilled workmanship requirement, etc. Welding is used in the construction of aircraft parts, automobile parts, building parts, pressure vessels, tanks, railroad equipments, ships, pipelines, and pretty much everything where cheap and strong metal-to-metal joining is required. The first type of welding is gas welding, which uses combustion heat of fuel gas mixture like oxygen and acetylene. A typical system consists of 2 cylinders, one with oxygen and other with acetylene. The flame of the torch is controlled by using a control valve. A filler rod is also added for increased strength. The flame reaches a temperature of 3200 degrees Celsius and thus can melt all commercial metals to form a complete bond. Gas welding has a lot of advantages like mobility, low cost, self-sufficiency, and a myriad of applications, but is limited by the time taken and skill required for perfect flame, storage of gases, health problems, etc. The second type of welding is arc welding. Here, welding heat is obtained from an electric arc between an electrode and the workpiece. The temperature ranges from 6000 degrees to 7000 degrees Celsius. Arc welding contains three important welding types, namely, first, submerged arc welding, in which the arc electrode is hidden under a blanket of flux. The continuously fed bay metal melts and acts as a filler rod. Advantages include high welding speed and smooth weld finish. Disadvantages include flux contamination. Second comes tungsten inert glass welding, or TIG welding. It is an arc welding process where coalescence is produced by heating the workpiece with an electric arc struck between tungsten electrode and workpiece. Advantages include better control on welding process with a drawback of high cost equipment. Third in line is metal inert gas, or MIG welding. Here too, coalescence is achieved with a metal electrode. Advantages include faster production speed, deep penetration with a compromise in complexity. Next in welding process is resistance welding. Here, coalescence is produced by heat obtained from resistance offered by the workpiece to flow off electric current in a circuit of which the workpiece is a part. The electrodes are mostly made up of copper alloys. Advantages include high rate of production, less skill requirement, but is limited by high equipment cost and special surface preparation requirement. The fourth type of welding is solid state welding. Here, coalescence is produced by the heat obtained from mechanically induced sliding motion between rubbing surfaces. Advantages include single operation, less time requirement, no smoke with a limit on dimension of workpiece. Fifth and last is thermochemical or thermite welding. Here, coalescence is achieved by heating with superheated liquid metal and slag resulting from chemical reaction between metal oxide and aluminium, leading to an exothermic reaction. Advantages include no electricity requirement but is only applicable for ferrous metal parts of heavy cross sections. Weld joints can be mainly classified as lap or fillet joint, butt joint, edge joint, T-joint, and corner joint. Weldability is defined as the capacity of metal to be welded under fabrication conditions, imposed into a specific and suitably designed structure, and to perform satisfactorily in the structure. The last part in welding is welding defects, namely undercut, cracks, porosity, slag incursions, and the lack of fusion. Their main causes being improper welding, base metal, and also wrong welding procedures. The second type of joining process is adhesive bonding, which is the process of joining materials by using adhesives. The adhesives used are mainly thermoplastic or thermosetting adhesives. Advantages include high joint strength, less localized stress concentration, and low cost, but is limited to the temperature below 177 degrees Celsius. Due to its ease of use, it is used primarily in all industrial and domestic applications. Third type of joining process is soldering, in which coalescence is produced by heating the rod to a suitable temperature and by using a filler metal with a melting point below 427 degrees Celsius. It is used widely in the semiconductor industry due to the simplicity and low cost. The fourth type of joining process is brazing. Here, metallic parts are joined using non-ferrous filler metal and is hence used in areas like pipes, heat exchangers, etc. The fifth and the final type of joining process is riveting, which is a permanent fastening method. There are 5 basic types of rivet heads, namely snap or cup head, pan head, countersunk head, half countersunk head, and conical head. Rivets offer almost no stress on the workpiece due to the absence of heat and hence require almost no skill, but require high amounts of cover plates to support the rivet. Hence comes the end of the quick revision of joining processes. Finally, it's time for this episode's question. What do you mean by coalescence? Also, it's time to answer our last episode's question. What are MTMs? MTMs, or multitasking machines, are CNC machines with many axes that combine turning, milling, grinding, and material handling into one highly automated machine tool. So, like
Steel is highly resistant to shaping when it's cold, and for that reason it is generally rolled whilst it's hot. To make sure the steel is at the correct temperature for rolling, it is fed into a furnace. Here it travels through several temperature control zones until it's at the correct temperature and ready for rolling. Whatever the product, the principles of hot rolling are the same. Steel is squeezed between rolls until the final thickness and shape are achieved. To do this, the rolls must exert forces of tens of millions of newtons, equivalent to a weight of thousands of tons. The rolls, therefore, run in massive bearings, mounted in housings of enormous strength and driven by powerful electric motors. These are known as mill stands. The layout of a rolling mill can vary from a simple single-stand mill to several stands positioned either side by side or in a line. The mill rolls themselves can either be plain for flat products such as strip, used for products such as cladding, or profiled for sections, beams and columns for use in construction. Mill stands have various roll arrangements depending on the product being rolled. The simplest arrangement is a two-high stand, used mainly for long products such as sections. For light sections and bars, three-high stands are sometimes used, with the steel passing one way through the bottom gap and back through the top gap. Four-high stands have two work rolls in contact with the steel, supported by larger backup rolls to prevent distortion caused by the rolling face. These give greater accuracy for rolling flat products, such as plate. Universal beam mills include stands with both horizontal and vertical rolls bearing on the steel simultaneously. The rolled steel is then cooled in a way appropriate to its end use and prepared for further processing or dispatch. One of the further processes is cold rolling of strip. This is used to produce a thinner, flatter product than is possible on a hot mill, down to a thickness of 0.15 millimeters. Forming properties and surface finish of cold rolled strip is better. It can also be coated with zinc to protect it from corrosion, with tin for cans, and with a plastic coating or paint for protection and decorative purposes.